So let's talk about the common challenges when it comes to securing ML. In this, I'm not going to talk about the typical software related security challenges because those are applicable for ML systems as well. Because at the end of the day, ML is getting packaged into software. But I'm only going to focus on something that's unique to the ML world. So, firstly, ML systems are highly data dependent. There's no doubt about that. So, the behavior of an ML system is influenced by the data that's used, obviously, the quality of the data, which is how clean or noisy it is, and whether the data can be manipulated. Uh, the second part around quality comes down to whether you can trust the uh, correctness of how the data is representing various real world patterns. So, the example here is labeling. So, if the quality of labels that you use in a supervised algorithm is good, then you can depend upon the data set to inform the ML model of the patterns that are of interest and the patterns that need to be set aside. But if the quality is not good, either because the labels are weak, which means not all the labels are correct all the time, or because the labels are intentionally wrong, and that's a separate class of attacks that are possible, then the model is potentially learning a behavior which is not intrinsic to the real world phenomenon. At which point, the model could be learning behaviors which the attacker wants it to learn, or the model is learning something completely random which is useless. And worse, we might not know it's useless as users of the ML output. We might still treat the classification as rock solid, but it's already moved away from being good quality. The third part that was mentioned here was whether it can be manipulated. So, if you think about the ML ecosystem, there are so many attack points that exist. So, these are points where the attacker can choose to infiltrate or make his or her presence felt in such a way that the end machine learning output is not correct. So, it can be at the data stage, that's what we're talking about now, where the data that's fed into the ML systems can be manipulated. And that typically arises when there is what's called as a third party dependency. So, in those kinds of cases, the data is not under your control as an ML engineer. It comes from some other source. And when it comes from some other source itself, it could be manipulated into having patterns that the attacker wants the ML model to learn. And as an ML engineer, where you just treat the data for what it's worth, you might not be able to differentiate whether the data has actually been manipulated or not. And that's quite dangerous. So, the traditional security models do not account for such kinds of attacks. They are called as invisible attacks because these attacks are not intrinsic to the code or the software, right? Because what do ML systems do? They're actually writing meta software where the logic for how patterns get interpreted is not expressed as programs, but is interpreted or is learned from data. And therefore, when the data changes and therefore the learning changes and the functioning of that software changes, the attack is said to be coming from an invisible angle, right? So, the traditional security methods that evolved for controlling software systems are not in a position to deal with such invisible attacks. The second angle here is model behavior is typically a black box. Like, in fact, even the best of deep learning networks that exist, that have been invented in academia, do not have a sound theoretical basis for it, where a formal system has come and proved that this is the reason why this type of an architecture works really well on these kinds of problem statements. And as a result, what you'll find is, unlike rule-based software, you do not have deterministic, explainable, predictable outcomes which are consistent. And therefore, you find that it becomes much harder to reason about such such systems which are dependent on ML. So you can't always predict why a model is actually giving the output it's giving, whether it's correct or wrong. And therefore, you might not be in a position to say whether it's been tampered with, either by um, having data change intentionally, or by having some other types of wrong data being fed into the training process. So in summary, you will see that defending a system that you don't fully understand is much harder, right? That's true in general, but definitely true for ML. A third problem which uniquely plagues ML systems is the fact that over a period of time, the underlying data on which the model was trained may no longer have the same properties. We're going to discuss this in depth in the next week's lectures. But in a sense, the ML systems need to evolve with newer data, either in terms of retraining or in terms of online learning, like which is sample by sample learning. But the problem is, as these systems evolve, the nature of the security problems also change. So maybe you worked really hard to secure the version 1 when the ML system first went live. But then as the system evolved, newer versions came in, 1.1, 1.2, etc. because the models got retrained. You continuously need to be in a position to secure all of them one by one. So therefore, instead of trying to secure individual models, which maybe you've got to do for only the production grade models which are promoted into the real world, you instead focus on protecting the training process itself. A fourth angle of challenge that's there in ML systems is that the artifacts no longer include just code or containers. It actually includes the model files themselves, the weights as a separate file, especially for deep learning networks. And those artifacts become, they have different kinds of management challenges than software. So one is the fact that the weights or the model file obviously could leak model information. So that's problematic. Second thing is that the weights could allow somebody else to take a look at the weights and reverse engineer a model, because obviously the weights will have the n cross m connections between two subsequent layers of a deep learning network. Likewise for all such subsequent layers, and the weights will also allow somebody else to reconstruct what that architecture looked like from scratch, and the extent of training, maybe the number of epochs that the model went through in arriving at a set of weights, along with the training data that was used. So the reverse engineering process is fairly easy if you have access to these artifacts, one or more of such artifacts. And therefore, like you could have malicious actors repeat the process and engineer wholly different kinds of systems and make it look as though it was published using the same process and same authorship, but now with completely different outputs. So the way that you might need to mitigate such issues is to have the artifacts themselves be subject to signatures, cryptographic signatures, that anybody else can independently verify. So much like you have software getting distributed using what's called as checksums, usually generated by cryptographic hashes or similar tools. Likewise for these artifacts also, when you ship them across, you also provide a signature so that when somebody else downloads that model and starts using it in their context, they can also verify the signature and say, look, whatever was produced is exactly what I have right now. Okay. The next challenge that's there typically for most newbie projects, meaning projects in ML which are done by rookies who are new to the ML world, is the exposing of that model API, and therefore the attack surface becomes larger. So what typically happens is like what we did with week 6, I think. We started with a model that we wanted to deploy, and then went into learning about containers. And as part of the learning, we deployed containers. We made our hands a bit dirty, and then we set up a load balancer on top of Kubernetes, and then the load balancer provides an external IP, and anybody who knows that external IP can then issue curl commands to get model outputs, right? Imagine now instead of working on hardening that layer before it gets exposed to the rest of the world or the rest of the company, the ML engineer is too eager to show off his work, and so he exposes that API, doesn't control it. So then what happens is that API becomes available for anybody to use, including malicious actors, and therefore they become vulnerable to adversarial examples, which slightly perturb, like I said, the input space, and that allows for model inversion to happen, or membership inference kinds of attacks to happen. The second angle is I could also make those APIs susceptible to probing, so that I know when it gets used by whom, and that becomes a challenge because then it could be a way to deny service to anybody who genuinely needs that API, but just at the point of need, you just bombard that API with a whole bunch of requests, which are much beyond the capacity of the backend server. Even with the best of auto scaling kind of functions that cloud provides, it still would result in impact, because there would be moments when the auto scaling has not kicked in, or in other scenarios, there are limits to auto scaling as well, right, in terms of resources available. So then the challenges would be from a perspective of how do you limit the rate of requests that come into that model service, monitor the service for frequent issues, frequently occurring issues, and then secure the gateway such that you don't have unauthenticated access to the ML model. So these are not typically out of the box available in machine learning pipelines. So you've got to think like a software engineer who works on security, not think of it as a data scientist, right? So these are two different perspectives. Then you've got the issue that plagues all new industries typically, which is the fact that there is no standard security benchmark that exists. This is unlike the world of software, where there is a lot of work that went into standardizing security. So much so that there are standards available for every language today from a perspective of writing software. Like for instance, OWASP, Stride, etc. But in the world of ML, there is no such single standard that everybody just subscribes to. In fact, there are, I think, active research that is happening on how do you standardize a bunch of benchmarks related to security, related to performance, related to model output and efficiency, etc. So those standards need to develop before everybody can have a single agreement on, what does it mean to ship out a secure ML system. So because there is no standard universal threat models that exist. Therefore, you're having to cater to a wide variety of interpretations that may be possible. This hinders the process of creating best practices, right? That's the problem with lack of standardization. So you've got pretty interesting tools which do specific types of attacks, but because the standardization does not exist, these tools are not general purpose, right? They work great in certain contexts. Like for instance, Clever Hands, quite an interesting name for a project. So it came from this, I would say, pop culture reference to a horse that was called as Hans, and the horse was supposed to be, really good at arithmetic. So the way it worked is, if you asked it a question, and the question was, arithmetic in nature, I believe, like simple sums, like 2 plus 3 equals 5 or things like that, then the horse would indicate whether it thought the answer was right, the answer that you were saying was right, by nodding its head or giving some visual cues. Or if you thought it was wrong, then it would give the opposite visual cue. So it became quite a TV sensation locally. I believe this was in Germany, if I remember right, where it was able to solve arithmetic. That's the way the media portrayed it. Turned out, what was happening was the person asking the question, I think it was the handler for the horse, he was asking the question with a certain pattern in the voice, and the horse was actually responding to the pattern more than the question itself. So if for instance, the person said 2 plus 3 equals 5, right? Like some such thing, right? The horse would say yes, because it's sensing that that intonation in the voice, because the user thinks it's correct, or user knows it's correct, the horse is sensing that intonation and then agrees to it. And it's doing the opposite when it's not sensing the intonation. So it wasn't a case of clever horses at all. It was just a case of, completely missing the point on how do you interpret standard horse behavior. But the point is, the researchers actually built a very interesting set of attack techniques or attack algorithms that built on this notion of incomplete or incorrect interpretation of outputs. So specifically, these tools like Clever Hands and Adversarial Robustness Toolbox, I believe that's from IBM. What they do is they help you construct examples of contrary behavior, adversarial behavior, and then pass that off as data set that the model needs to get trained on, right? Or the model exercises its judgment on, and then you will find that with such adversarial examples, the outputs become all over the place. So part of the reason is there's no standardized security benchmarks that people can just adopt and know for sure that no such adversarial impact is possible. The other angle that's very unique to ML is there are attack types which have not been researched as comprehensively as the software related attack types. Like one of the most common database attacks that are possible is something called as SQL injection. What it does is it allows for the attacker to inject malicious code inside the SQL, especially very long SQLs, and send it in as an SQL query like a select statement. So for the casual observer, or basically the simple kind of security implementations that might exist, it might conclude that this query is fine because it's just a select statement, it's not going to modify anything. But because the select statement is really large, the backend's database service might fail because it's not equipped to handle that bigger select statement. And when it fails, it overrides or it gets access to certain parts of the database memory that it won't normally provide access for the user. So when that happens, it typically happens on exception behavior like a crash or something like that. Then the code that exists in that SQL that's been inserted by that attacker will have a chance of getting executed, and the code will be a way to take over the system. So SQL injection attacks have been known for quite some time, and almost every database that you see today in the world that gets shipped out goes through extensive analysis of whether it's susceptible to SQL injection attacks. So that's an example where the threat class is known for a long time, and there are many solutions that exist to deter it. But because the threat classes for ML are new, an equal amount of research or mitigation mechanisms do not exist. So we saw some examples already: data poisoning, evasion, membership inference, model inversion, etc. Last but not the least, like with all complex systems, you've got so many different stakeholders coming together in a typical real world ML. But the problem of ML is even more daunting because the kind of skills that are required for putting together an operational system is much more. So you've got obviously the data scientists and ML engineers, folks like you and me, but you've also got people in the DevOps line of work, IT security. Half the companies in the world, okay, that half may be an exaggeration, but most of the companies in the world use some form of external vendors to help out, and those external vendors help out in very specific ways. Like there's a vendor for cleaning data, there's a vendor for building a data lake, there's a vendor for building models, there's a vendor for managing your cloud, etc., etc. So when you've got so many third-party actors coming together for the same system that goes live, you end up having problems of communication, problems of what assumptions are made by certain users which are actually violated by somebody else because those assumptions have not been ever communicated in formal mechanisms or formal means. So each team that works on or touches the elephant introduces a certain risk to that elephant, right? So that kind of a problem exists in these multi-party, multi-stakeholder kind of systems. Okay, so let's take a look at how you can go about securing your ML code. This part of the discussion might not be um, as straightforward as typical ML type of content. So let's go through it slowly with examples as well. Yeah, so I'll meet you on the other side of the video.